Okay, should we get the show on the road? Okay, so the goal, which I will really not get started on until next time, is to do multidimensional wavelet theory. And basically, what I'm going to do today is to describe a method which is not unrelated to what we did here, the way the Walshes and the relationship between the Walshes, where the 2 to the n minus first Walsh was equal to the nth rounding. And basically there was a very basic theorem in analysis, which very deep theorem in analysis, which we talked about earlier, Amy Carlson's theorem, was proof of the Lucene conjecture. And the way that transpired, well, Carlson's a genius, so, no, but an intermediate step came from Kolmogorov, who also was a genius. And in the 1920s, he constructed an L1 function on 0, 1, whose Fourier series diverged everywhere. Now that's sort of fascinating because you can integrate Fourier series no matter what the convergence. You get meaningful results. But at the same time, he also proved a positive result. And he proved the following result. He proved, so this is Kolmogorov. We take F in L2 of the torus, and you let Sn be the nth partial sum Fourier series. That implies that the limit S 2 to the n of f of x is equal to f of x. So basically he was looking at Sn of f is the symmetric sum . So he proved this result and it's what one would like given the Lucene conjecture. And the Lucene conjecture proven by Carlson just replaces the 2 to the n here by an n. But doing this thing by Lachenary jumps made all the difference in the world, because this is quite simple with respect to Carlson's proof. Now, what we're interested in is and I'm going to go into some detail about this next week. If you do a multi-resolution analysis, a dyadic multi-resolution analysis, and you're in RD, then what's forced upon you is you essentially need, and I'll write out the results more clearly next time, you essentially need 2 to the d minus 1 wavelets. And so for many years it was thought that even though on the real line this wasn't the case, it was thought that you couldn't get one wavelet to be an orthonormal basis for LD when D was bigger than 1. I said part of that incorrectly, but the fact is people did not think that you could have just one wavelet in L2 of RD, D bigger than 1. Wavelet being, when you look at its dyadic wavelet expansions, they're going to form an orthonormal basis. And then all of a sudden came this crowd from Texas A&M, for which I've been recruiting vigorously ever since. And we now have 2 graduate students from there. Anyhow, great guy there, Dave Larson, and Shinda Dai, and then Darren Spiegel, very early on. They didn't know exactly what they were doing. I say that as a compliment. They came at this subject in using functional analysis, rather abstract functional analysis. And then after a while, they realized that they had proven that, in fact, in L2 of RD, you could construct a function whose dyadic, when you look at its IMNs, the 2 to the m d over 2 psi of 2 to the m x minus n, okay, where m is in z and n is in zb. So they showed you could construct one function psi so that this was an orthonormal basis for L2 of RD. I must say, I realized right away, because I had been studying wavelets for quite some time, that they had done something special, and I basically grabbed their first paper to publish in the Journal of Fourier Analysis and Applications, but also got caught up in the subject, and as did a number of other people, because their analysis was, as I say, more in the realm of abstract functional analysis. And the idea was, well, could you make these things pretty? Could you make these functions computable? And so, in that sense, we're going to do right now some constructive, some d-dimensional harmonic wavelet theory, but it's not the systematic part. It's definitely the non-multi-resolution part. And next week we'll come in with the more classical theory and do the MRA part. But this part here is fascinating. And there's still a lot of mileage to do it. And so basically, we wanted to have a systematic way of constructing such wavelets that Larson and Shinda Dai and eventually Darren Spiegel. And so, let K0 be contained, and I'm just going to give a sort of one of our primitive versions since it's more down to earth, be in minus n and the d be contained in R at d, be a neighborhood of 0 with Lebesgue measure equal 1. And I want to assume certain things. Definition. If I take A and B contained in R at D, we're going to say that A and B are tau congruent. Now, tau here is simple, it just stands for translation. I mention that because one of my first jobs ever, I worked for the Radio Corporation of America. Well, my first job, I was a soda jerk and delivered mail, and used to call up people to collect their bills, which was a Not my style. But anyhow, my first technical job, one of my first technical jobs, was we were working on the early warning system, and it's amazing these things ever work, knowing that I worked on this stuff. But, some of our failures were great. We discovered when we were testing it, we actually had an alert, but it was the moon, so that was not considered a big threat at the time. But for a while there, we said, "This is a threat." But we worked it out of the Burlington plant, and we were doing some really nice work, sort of applied Newton's laws, basically. But there were some numbers that were very complicated, and they brought up all these engineers from Moorestown, and zillions of people around there. And the final word of the day was we changed a very natural type of a unit to erads per tau. That's good for Earth radians per something of a second. But instead of feet per second or something, we changed it to erads per tau. It's obviously had an impression of how stupid that was. Okay, A and B are tau congruent if there exist countable partitions AP, P and Z, and BP, P and Z, of A and B respectively, and there exists a sequence NP, P and Z, that these NPs are in ZD, such that for all P in Z, AP is equal to BP plus N. Okay? And basically, tau congruence is all over the place. There are lovely results by the Lat and Wavelet theory. It arises in our work on uniform sampling in higher dimensions and in groups. So it's a natural motion.
Do these partitions have to be measured?
Yes, everything has to be measured. Yeah. Sorry. Otherwise we get into Banachowski land, I guess. I should have said measurement. Sorry. Now, this is a basic result which several of us realized independently, but it's so elementary, it doesn't matter. But I'll write it down as a theorem. So let K contained in RD be measurable with the properties that K is tau congruent to minus a half, 1/2 to the D. So that's nice unit neighborhood of the unit measure neighborhood of the origin. And this guy here, 2 to the M K, where M is in Z, is a tiling of R hat D. Now, note K tau congruent to minus a half, 1/2 d is equivalent to k plus n, where n runs through zd, being a tiling of r hat d. Now by tiling, I mean good tiling, namely they cover the surface completely and they don't overlap except to the set of measure 0. Now, if you have those two properties, set psi hat to be the characteristic function of k, then psi mn, as defined on the other board, is an orthonormal basis for L2 of RD. Well, there you go. It's all done, right? Now, except that those two conditions are really weird, right? I mean, to have a tiling in the usual way, like your usual square tiles, or maybe even a fancy hexagonal foyer tile, is one thing, but to have that same block have the property that when you raise it to powers, it's also going to be a tiling, is counterproductive. I mean, counterintuitive. And so it's not at all clear that such sets exist. In some sense, it has to both be a square and an angles. And so basically, we proved that not only such sets exist, and that's of course what Larson really understood with Shinge, but we have a machine that makes them, and that's what I wanted to show you, how to make these guys. Okay. I must say, I think there's still some legs with this business, and I tricked Emily about a year ago into this subject, and we've written a paper which I will allude to a little bit later on. There is a very nice result, but I think there are also other very nice results in this area. And I think it's really worthwhile in this era of dimensionality reduction, because the data we get is so big that if you're dealing with high dimensional spaces, it behooves us to be able to represent all signals in that space by, if you're in a d-dimensional space where d is the distance from here to Sirius in millimeters, it behooves us to have a signal decomposition theory where you don't need so many harmonics in order to represent your signals. And the bottom line here, I'll tell you the punchline right off the bat, we can construct these wavelets, and that was done with Manuel Leon and Songyatsu Kijikawa. And as I say, other people have been involved with this too in other universities, but I think our machine is very down and dirty. It's very mechanical. But the sets are very complicated. So the project that Emily and I did was based on a little theorem I proved with some Kijikawa. You could do it with very simple sets also. I'll show you those. But you lose orthonormality, but you can do it with frames. And so this this idea of using frames is very good in dimensionality reduction in many ways, and this is another way for very high dimensional spaces. Okay. So I took a set K naught, which was enabled at 0. I wanted it to be measurable. Well, let's enable it. And I'm assuming that it's assume K naught is congruent to minus a half, 1/2 of D. And now we're also going to take a mapping, choose a measurable injective mapping T from K naught. K naught is in minus n to the n D into minus 2n D, take away minus n D. This turns out to be a technical constraint. It is not absolutely necessary, but it helps fix things in our mind. And we want, with the property, that for all gamma in K naught, T of gamma is equal to gamma plus K sub gamma for some K sub gamma in ZD. I'll give examples to show you what's really going on here. But when I realized that we needed this is going back to the work with Leon, I immediately thought of Maurice Escher, because this is how Escher made his pictures. Okay. Now, as a little fact associated with this, the reason I need things measurable, so proposition assume T is measurable. That is T inverse of U is Lebesgue measurable for any Lebesgue measurable set U. No, just a measurable. I don't need open. No, I'm just doing measurable sets. T inverse is measurable. I'm talking about measurable mappings. So I know for open as usual for how we define it, but here I'm defining measurable just to transform measurable sets in the range into measurable sets in the domain. That's all I need. For any Lebesgue measurable set U in the range of T. Okay, so assume T is measurable and injective one-to-one on K0, then T is measure preserved. Yeah, I shouldn't, that's a bad term, I guess, but that's what I mean, though. Yes, yeah. I mean, I basically have to have the measure preserving this. And this definition here, the Escherness of it is exactly what Escher did when, you know, he started off with some object, and then he sort of moved things around. He's somehow, you know, be able to start off with a square and end up with something that had the same measure as the square, but could end up looking like a frog. Okay, so we need that fact. I usually complain about soft chalk, but tonight that chalk's getting too hard. Okay, so for the construction, we have a set K0. It's a little bit complicated, but when we thought about it enough, it was a natural thing to do. Let A0 be equal to K0 intersection, and now I'm going to take the union of 2 to the minus j K0 for j bigger than or equal to 1, and K1 equal K0 take away A0 union T of A0. And so that's why I'm keeping the measure the same by doing this. Okay? I'm keeping the measure the same. And so then, by the way I define things, then K0 take away A0 puts us in K0, which is in minus n to the d. And T of A0 is contained in minus 2n to the d, take away minus n. We're moving things around. Question? Oh, thank you. Okay, there's A1, A0. What's A1? A1 is going to be the same sort of thing. A1, let A1 be equal to K1 intersection the union of 2 to the minus j K1 with j bigger than or equal to 1. And then we can define K2. And K2 will be equal to, and now here I took away A0 from K0. I'm going to take away K0, take away A0. Take away A1. And then I'm going to add to that the union of T of A0 union T of A1. So you sort of get the idea what's going on. And once again, and I won't repeat it after this. Once again, we have the then K0 take away A0, take away A1, it's certainly contained in K0, and this guy here, T of A0 union T of A1, is going to be contained in this rectilinear annulus here. minus 2n, 2n d, take away minus n, n to the d. Just the way I'm cutting things up. And so, notationally, we set an equal to kn, intersection of the union of j bigger or equal to 1 of 2 to the minus j kn. Okay. And then we set then k n plus 1 equal to, and I'm just going to abusive language here, but k0 minus a0 minus a1 all the way down to take away an union, the big union of t of a0 union t of a1 all the way up to union t of an. So I've got my ANs and my KNs, and I've got the same sort of inclusions that I wanted. And now we write down K. Okay. So K set, can you see up here, Brent?
Mm-hmm.
Set K equal to the intersection n equals 0, 1, etc. of k0 take away a0 take away all the way up to take away an union, and then we have the union from n equals 0, 1 all of the t of the ANs. So that is my set K, and that set K doesn't. K has these properties. It's congruent to that, and the dilations are going to be a tiling. And that was our first result in these matters. Just as an example to show what happens here, I say we, all of my co-authors generated fantastic examples by means of computers. But the general idea is to do the Escher mapping. So let me just draw one. Let's just take, we can take for K0 any neighborhood of the origin of measure 1. But let's take let's just take this guy here. In the plane for the moment. And that'll be my K0. And now I've got any old n, capital N. So let's look at this n. And basically, I'm going to do this. Okay, so my set is in here. I mean, this is in. Well, if pad of K0 is here, I'm going to move it. Let me just write down the rule here. It's 2n minus 2n. So no matter what pad of my neighborhood is in here. I'm going to move it over 2n and down 2n. So I'm going to bring it down here. And it's going to go in there, etc. And so I'm really doing the Escher map. That's to say, moving things essentially modulo some lattice. Now, basically, you've got to continue this game over and over again in order to get a wavelet set. That is to get, say, get an orthonormal basis. And the sets one gets, these Ks, these final Ks, are, well, they're just messy. They look like fractals, but they're not fractals. But they're fractal-like in nature. And so there are lovely theorems, they're nice computer simulations, but they're not very implementable. And at one point when I was talking about some of these things, I had the good fortune of having Eric Weber in the audience, who also had a A&M connection. Did you know him at all? Maybe you'd already left. Anyhow, he was a postdoc with David, I think.
Yeah.
But in any case, he just said, well, what can you do about frames? And I hadn't even thought about that. Obvious question to ask me, really, but I hadn't thought about it. And so Sonia and I did think about it, and without going through any of the mathematical background of it, we verified the following result. So, theorem. For each n bigger than or equal to 0, kn, take away an, is a Parseval wavelet set, and Kn is a frame wavelet set with frame bounds 1 and 2. Now what does this mean? Well, basically a Parseval wavelet, so K is, let me call it L. L is a Parseval wavelet set if psi L hat equals the characteristic function of L, and for all F in L2 of RD, the sum of F psi L Mn quantity squared is equal to F in L2 quantity squared. So it's a gives rise to a frame with very nice bounds. And frames give decompositions. It's not an orthonormal basis, but now these sets here, I could take K0 minus A0. I have really simple sets now. And I'm getting passes all frames and I can compute with them. And I can be in R10 billion and generate every signal in L2 of R10 billion in terms of one frame rate. And just to let you know what the project basically Emily and I did was one would like to have good temporal behavior too. And because these are characteristic functions, you'd like to smooth them off and still get wavelet sets. And that's what we did. Okay. So I think I'm going to close for the night. Next Monday and the following Tuesday, I'll do the sort of conventional standard MRA theory in RD. It's fascinating, and I don't think I can do justice to it in 2 lectures, but you'll see some of the complexity that arises